In these videos, I'm going to discuss Poisson and negative binomial regression and how to carry those analyses out using SPSS. For starters, let's look at some background information. So, Poisson regression is utilized when a researcher has count data on some dependent measure that represents the rate of incidence of some event. A rate of incidence can occur within a certain time frame, such as the number of traffic accidents at an intersection over a 30-day span, or within a certain geographic or spatial unit, such as the number of children in a family. As you can see, Poisson regression relies on the Poisson distribution, which is actually a family of distributions. Each has its own mean and variance. However, it should be noted that essentially the special thing about the Poisson distribution is that the mean and the variance are equal. So you'll notice that the mean is denoted by lambda, and so each of these distributions that you see in these different colors have different means associated with them. And as you're looking at this, you can see that as the mean for those distributions with means that are closer to zero, you can see that they tend to be more skewed and more peaked. And you'll also notice that they also have less variation. As the mean and variance increases from zero, you'll notice that again the variation is getting larger. And also you'll notice that the distributions appear increasingly normal in shape. So what this means is that the Poisson distribution is probably most useful when dealing with data involving rarer events, such as the number of car accidents in an intersection over the span of 30 days, where the mean is closer to zero. For less rare events, where the mean and variance departs more substantially from zero, then the normal distribution may be a reasonable distribution to utilize when estimating the probability of a particular count outcome. So as noted earlier, the Poisson distribution is very useful when working with a count variable. However, when working with this distribution, you are assuming that the mean of the distribution is equal to its variance. When the variance of a distribution is greater than its mean, the distribution is said to be over-dispersed. And also, when the variance of the distribution is less than its mean, the distribution is said to be under-dispersed. But the fact of the matter is that over-dispersion tends to be the more likely scenario when you're actually dealing with data. So over-dispersion often, but not always, occurs when you have a large number of zeros in the observed data stemming from very low frequency events. It can also occur when there are large counts in the upper tail of the data distribution. So an alternative strategy for modeling over-dispersed data involves relying on the negative binomial distribution. So it has the same sample space as the Poisson distribution, but has an additional parameter that is used to model the variance. This parameter is referred to as the dispersion parameter. So here we have an image providing a comparison of Poisson and negative binomial distributions, assuming that they have equal means. So you'll notice that the probabilities, or the relative frequencies, for different values in these two distributions differ. Even though they look fairly similar, there are some important differences. So you'll notice that around the center of this distribution, around the mean, the relative frequencies for the Poisson distribution tend to be higher than the relative frequencies that you would observe with the negative binomial. And then as you move out into the upper tail, the relative frequencies for the negative binomial counts in the upper tail tend to be higher than the relative frequencies that would be observed with the Poisson distribution. So the aim of negative binomial regression is the same as that of Poisson regression, which is to model relationships between predictors and the likelihood of certain count outcomes. The probability distribution that is utilized, which is the negative binomial distribution, takes into account the issue of over-dispersion in your data. Okay, so now let's get to looking at some data. So here's a scenario. Let's say you are a counseling researcher studying predictors of the number of client no-shows over a 3-month period. You collect data from a set of 40 clients at a community mental health center on the number of no-shows over 3 months, each client's sex, which is coded 0 for male, 1 for female, verbal ability, and the tendency to avoid disclosure of personal information. Both of these are assumed to be continuous measures. And primary method of transportation when it comes to attending sessions. This variable coded 1 for personal transportation, 2 for public, and 3 for other. So here is our SPSS data. It's actually hypothetical data, so at any rate, we have data for 40 individuals with our variables verbal ability, avoidance, no-shows, sex, and mode of transportation. So just kind of looking at the measures, the scales, you can see we have verbal ability, avoidance, and no-shows treated as scale variables. Nominal sex and mode of transportation are treated as nominal variables. So to run the Poisson regression in SPSS, we have to utilize the Generalized Linear Models module. So we'll click on this, and this box will open up. And so this has various GLMs, or Generalized Linear Models, that you can select from. And we are going to select on Poisson log linear. So in terms of what we have to do is, in terms of model specification, we have to specify our dependent variable, which is no-shows, and our predictor variables. We have verbal ability, we have avoidance, and we have sex. Sex is a dummy-coded variable already. It's coded 0 for male, 1 for female, so we can go ahead and include that as covariates. Mode of transportation is a little different. Even though sex is a nominal variable, but like I said, it's already been dummy coded, whereas mode of transportation has not been dummy coded or not been converted into dummy coded variables. So we have to ask SPSS to do this for us. So we move mode of transportation over to the factors box, and I'm going to go ahead and click on, under options, I'm going to click on descending, and then continue. Now, really, just briefly, let me just kind of note what I'm asking SPSS to do. Essentially, if we want to model a predictor variable that has more than 2 levels associated with it, and that predictor variable is categorical, then we have to create dummy-coded variables in order to capture the information that's contained in the original variable. So we can either do this the easy way, which is to allow SPSS to do this, or we can do it the harder way, which is to do it manually. And I'm going to go for the easier way. But nevertheless, let me just kind of show you what I mean when I talk about dummy variables. Essentially, our original variable, mode of transportation, has those 3 levels associated with it. And so the value codes were 1, 2, and 3. So, to include this variable in the regression analysis, this information has to be recoded into a set of dummy variables. And basically, if you have a categorical variable, the number of dummy variables that are created is the number of groups or number of categories minus 1. And that's really the reason why sex, we can go ahead and include this here, is because we have 2 categories, male and female, minus 1, which gets us 1. So that's obviously we are left with 1 dummy-coded variable here. So that's the reason why we didn't actually have to ask for SPSS to do anything for us. It's already been done. But nevertheless, with respect to our mode of transportation, we have to do the following. We have to select a baseline or a reference group to compare each other group against. And essentially what's going to happen is that in the regression, the dummy variables are going to capture orthogonal contrasts between the different groups. So by selecting descending, I'm essentially having SPSS code the group with the lowest value, which is the personal transportation, with values of 0 on both dummy variable 1 and dummy variable 2. The second category, public transportation, will be assigned dummy values of 1 and 0, and then the third group will be assigned dummy values of 0 and 1. So essentially, the first regression coefficient or the regression coefficient for the D1 variable is essentially a comparison between group 2 and group 1. The second regression coefficient the regression coefficient for the second dummy variable is a comparison between group 3 and group 1. So that's essentially what's happening. If I had selected the ascending option, then essentially group 3 would have been treated as the reference or baseline category. We would still have group 2 being coded 1 and 0, and then group 1 would be coded 0 and 1. So, but we didn't ask for that. We've asked for this situation right here. Okay, so under model, we have to specify which predictors we want to include and so forth. So we're going to move each of these predictors over. If I wanted to model an interaction between two of the predictors in terms of accounting for variation in the count variable, I could click on interaction and then just highlight those two variables and move it over, and it would create an interaction term. I'm not going to go any further with this, and actually I'm going to take this out because just to keep things simple in our example. So under estimation, we have a number of defaults. Under statistics, I'm going to click on include exponential parameter estimates, and what this is going to be doing is it's actually going to get me what is called an incidence rate ratio, and I'm just going to abbreviate it IRR. And it's interpreted this really in large part the same way that the odds ratio is interpreted in logistic regression. It's just that we're going to call it incidence rate ratio as opposed to an odds ratio. Under save, we can click on predicted values. This will generate predicted count values, and then we also have predicted value of linear predictor. That is actually, we can click on that, which is really getting at predicted values or predicted log counts, and I'll talk a little bit more about that in a bit. And then we can click on request residuals. So one type of residual we can click on is deviance residual. So next I'll click on OK, and we have our output. And so you'll notice, first of all, the model information in terms of the probability function, it's a Poisson distribution. And then we have what is called a link function, and it's log. And essentially what's going on is that if I want to predict those no-shows or count of no-shows, I can't use least squares regression because essentially the relationship between the predictor variables and those counts is nonlinear. So the way around this in generalized linear models is to utilize what is called a link function. So, and the link function is this essentially allows for a modeling of a linear relationship between the predictors and essentially a transformation of the values of the dependent variable. So when we talk about the relationship between the predictors and the dependent variable, looking at the regression coefficients, we're going to be talking about log counts as opposed to counts. Okay, so scrolling down, we have our Omnibus test, likelihood ratio chi-square test, and basically this is a test of the fit of our model, our full predictor model, over a null model. A null model containing no predictors. So essentially, if the p-value that is printed out, if it is less than or equal to the alpha level that you set, and by generally speaking, people adopt a 0.05, but you can obviously increase or decrease it, but this is the conventional standard. If p is less than 0.05, then we would say that our full predictor model represents a statistically significant improvement in fit over the null model, and that seems to be what we have right here in our data. Okay, so if we scroll down a little bit further, we have a table of parameter estimates, and basically the reasoning associated with these two tests, the Omnibus test and the parameter estimates test, really follows the same logic that we have when we're running least squares regression, and that is we want to know, first of all, if the overall model is statistically significant, meaning are the predictors really accounting for significant variation in the dependent variable? And that's what the Omnibus test does for us. And if it does, then we move on to look to see which of the individual predictor variables are uniquely accounting for the variation in the dependent variable. So that's where we use the parameter estimates to unpack which predictors are really driving the overall association between the predictors and the outcome variable that we saw with the Omnibus test. So you'll notice that we have our various predictors. We have verbal ability, we have avoidance, we have sex. You'll also notice that we have these other variables for 3, 2, and 1, and you'll notice that essentially with the 1, this column right here contains regression coefficients, unstandardized regression coefficients. And you'll notice that this value right here is 0, and the reason why is because no regression coefficient is being computed here. Essentially what's going on is that this is essentially the first dummy coded variable I was telling you about. This is basically our D1, and this is essentially D2 right here. So for the first dummy variable, it involves a comparison between the group coded 2, which is the public transportation, versus the group coded 1, which is the personal transportation. And for the second dummy variable, it's the group coded 3, which is other, versus the group coded 1, which is the personal. So the group 1 is really the baseline group. So that's the reason why there's no regression coefficient here or anything of that nature. So if you want to just sort of ignore this, that's probably not a bad idea. But just keep in mind that these are basically involve comparisons between the latter two groups and the baseline or reference group, which was group 1. Okay, so in terms of interpreting the regression coefficients and so forth, let's start with verbal ability. And the regression coefficient is negative 0.032. Now, as I noted previously, if we were using linear regression or least squares regression, we would be interpreting this to mean for every 1 unit increase on verbal ability, there was a certain amount of raw score unit change on the dependent variable. In our case, our dependent variable is a count variable, and like I said, the relationship between the predictors and the counts on our dependent variable are inherently nonlinear. So it's nonlinear. And what that basically means is that least squares regression is not appropriate. Now, we can still model the relationship between the predictor or predictor variables and the dependent variable using a linear function, and that's where the log link comes in that we saw previously. So if I sort of just kind of scroll up a bit here, that's where the log link comes in. So essentially, when we're interpreting our verbal predictor and our regression coefficient for it, we would say for every 1 unit increase on verbal ability, there was a decrease of 0.032 on the log count of no-shows. So we're interpreting this in terms of log counts rather than in terms of the actual number or actual counts. So essentially, when we're looking at the regression coefficients, we're talking about the change in log counts That's delta log counts for every 1 unit change or increase on the predictor variable. I know you can't read this, but just kind of work with me on this. So at any rate, that's what that means. So we see, so this is basically telling us that people with higher verbal ability tended to have lower or fewer no-shows. Now, is this a statistically significant finding? Well, we utilize the wall chi-square test. There's our chi-square value, degrees of freedom, and then we have the significance level. And so the significance level, essentially, again, these are p-values, and we're comparing them against a stated alpha level. And so we're looking to see if the p-value is less than or equal to the alpha level that's stated, and oftentimes we just kind of adopt the conventional standard of 0.05. So if we were using that particular standard, what this is basically telling us is that verbal ability was not a statistically significant predictor in our model. We can, let's look at avoidance. So with avoidance, we have a regression coefficient of 0.077, which would mean that for every 1 raw score unit increase on avoidance, we have an increase in log counts of 0.077, or the predicted increase in log counts is 0.077. Is this a statistically significant predictor? Well, there's our wall chi-square test, there's our degrees of freedom for the test, and we see that here our p-value is actually less than our alpha level, which we had stated was 0.05. So in this case, we would reject the null and we would say essentially that avoidance was a significant predictor in the model. Let's look at sex. We had coded females as 1 and males 0. So if females are coded 1 and we have a negative regression coefficient, what that's basically telling us is that females would have a lower log count in terms of no-shows than males. And in fact, the predicted log count for females is 0.488 units less than the predicted log count for males. So as you can see, sex is based on our coding is negatively related to the log count of no-shows. Now, is this a statistically significant finding? We see that our p-value is actually less than our stated alpha level at 0.05, so we would reject the null and we would conclude that sex was also a significant predictor in the model. Now, this column right here, the EXPB column, this is basically capturing incidence rate ratio. So I'm going to call this IRR just for short, because it's really hard to write that out in full using this little pen tool. So it's an incidence rate ratio. And essentially you're interpreting it very much like you do with the odds ratio in logistic regression. So a value of 1 basically means that, or would be interpreted to mean, for every 1 raw score unit increase on the predictor variable, there's essentially no predicted change in the incidence rate ratio. Essentially, and that would basically, let me just kind of write this back up here. So if it equals 1, that essentially means, so if IRR is equal to 1, that essentially means that we do not have a relationship between the predictor variable and the incidence rate in terms of the count variable. So the incidence rate is neither increasing or decreasing. If we had an incidence rate ratio of 1, that we would also have a regression coefficient that would be equal to 0. So our regression coefficient would actually equal 0. If we have an IRR that is greater than 1, what that means is that as scores on the predictor variable are increasing by 1 unit, then the incidence rate ratio is increasing by a factor that's greater than 1. And so essentially we would also have a situation where our regression coefficient would be greater than 0. If our incidence rate ratio was less than 1, then that would be a situation where, as scores are increasing on the predictor variable, the incidence rate is actually decreasing. And in terms of the regression coefficient, we would expect to see a regression coefficient that is less than 0. So, as you can see right here, for verbal ability, we had a negative relationship between verbal ability and the log counts, and you can see that the incidence rate ratio is 0.969. So, in other words, the incidence rate in terms of the number of no-shows is decreasing as verbal ability is increasing. However, again, this is not really a statistically significant finding. But we could also, talk in terms of the percentage of decrease in the incidence rate for every 1 unit increase by just using the following strategy. So if we have, in this case, we could say, 1 minus 0.969. Okay, so essentially, what we would have is 0.31. Or rather, it should be 0.031. 0.031. Let me just write this out a little bit better. 0.031. And so if you multiply this by 100%, what that would tell us is that for every 1 unit increase on verbal ability, the incidence rate in terms of the number of counts of no-shows is decreasing by about 3.1%. So that's how you can interpret that. For avoidance, we have an incidence rate ratio of 1.080. So in this particular case, we would say, essentially we could say for every 1 unit increase on avoidance, the incidence rate ratio is actually increasing by a factor of 1.080. So if we want to talk about the percentage change, we can just say 1.08 minus 1, which obviously leaves us with 0.08. And if you multiply that by 100%, then you would have 8%. So for every 1 raw score unit increase on avoidance, the incident rate ratio increases by 8%. For sex, you can see that we have an incidence rate ratio of 0.614. So in this case, we would say for basically that we would be saying that the incidence rate for females, so we'd say 1 minus 0.614 is equal to 0.386. So we'd say for females, basically the difference, basically females, the incidence rate is 38.6% less than the incidence rate for males. Okay, so now let's take a quick look at the mode of transportation predictor variables. So remember, this is D1, our first dummy variable, and D2 for the second one. And so as you can see right here, our regression coefficients are actually positive in both cases. So basically, folks in the public transportation who had public transportation as their primary mode, the predicted log count was 0.397 points greater than those in the or units greater than those in the personal transportation situation. Those whose primary transportation is other, the log counts is 0.255 units greater than those in the personal condition. And you can see right here that that essentially neither of these were significant if we adopt the p-value or adopt the significance level of 0.05 to reject the null. This one's more in the ballpark, but it's still not statistically significant at the 0.05 level. Nevertheless, you can see that the incidence rate ratios are also reflecting the fact that that there's a greater incidence rate of no-shows for those individuals in the public whose primary transportation is public or other as opposed to personal. So the incidence rate for those whose primary transportation is public is about 1.488 times higher than the incidence rate for those whose primary mode of transportation is personal. The incidence rate for those whose primary transportation is other is about 1.29 times greater than the incidence rate for those whose transportation is personal. The last thing to kind of note in this, or actually a couple of other things to note in the this output, you'll notice that you've got this little test of model effects here with the wall chi-square test and the significance levels and so forth. And really, what you'll notice is that for our predictor variables that were already dummy coded, the p-values and so forth and the wall chi-square values, they were all exactly the same. The only difference really is with our categorical variable mode of transportation that happened to have 3 levels, and so it was not already dummy coded. And so this is just kind of a test of the overall effect of mode of transportation without breaking it out into the dummy variables. So at any rate, probably this set of estimates is more informative, but this is most of these estimate effects will mirror what we saw with the parameter estimates. The only difference was how we treated our categorical variable that had more than 2 levels. Okay, the last thing to note on this particular analysis is the goodness of fit output. And essentially, this is most useful when you are comparing different models, say models that have different sets of predictors, or later we'll talk about negative binomial regression and the fact that it includes a dispersion parameter in it, and so essentially this is useful for comparing different models that have been specified in different ways. So probably the two biggies in terms of being able to assess comparative fit between different models is Akaike's information criteria, or information criterion, and Bayesian information criterion. And basically, if I had another model that I was comparing this model against, the preferred model would be the one with the lower AIC and BIC values. Okay, so that concludes this discussion about Poisson regression, and the next video is going to continue this analysis and utilize negative binomial regression.